Quantum computing is a rapidly evolving field that leverages the principles of quantum mechanics to perform computations in ways that classical computers cannot. Traditional computers process information as binary bits, which can be either 0 or 1. Quantum computers, on the other hand, use quantum bits or qubits, which exploit quantum phenomena such as superposition and entanglement to represent and manipulate data more efficiently. Core concepts in quantum computing: classical bits versus quantum bits. Qubits. In classical computing, the smallest unit of information is a bit, which can exist in one of two definite states, 0 or 1. All the data processed by classical computers is encoded in these binary values. A qubit, however, is the fundamental unit of quantum information. Unlike a bit, a qubit can be in a state of 0, 1, or any combination superposition of these states simultaneously. This is due to the principle of quantum superposition, making qubits exponentially more powerful than classical bits in specific computational tasks. Superposition. In classical systems, an object can be in only one state at any time. In quantum systems, superposition allows a qubit to exist in multiple states at once. For example, a qubit can be in a combination of both 0 and 1 states at the same time, which provides quantum computers with parallel processing capabilities. The ability of quantum computers to leverage superposition is one of the primary reasons they can outperform classical computers in solving complex problems, especially those involving large datasets and numerous variables. Entanglement. Entanglement is another quantum property that plays a key role in quantum computing. When qubits become entangled, the state of one qubit is directly related to the state of another, even if they are separated by vast distances. Changes made to one qubit will instantaneously affect the other. This non-local connection between qubits allows quantum computers to process and correlate data across multiple qubits far more efficiently than classical systems, where each bit operates independently. Quantum interference. Quantum computers rely on quantum interference to enhance the probability of obtaining correct solutions. Interference can amplify desirable quantum states, leading to the correct solution, and cancel out unwanted states, leading to incorrect outcomes. This fine-tuning of quantum states makes quantum algorithms like Grover's search algorithm and Shor's algorithm highly efficient compared to their classical counterparts. How quantum computers work. At a high level, quantum computers use qubits and leverage quantum mechanics to solve problems by evolving the quantum state of the system. Unlike classical computers that follow deterministic algorithms step by step, quantum computers manipulate probability distributions across multiple states to converge on a solution. Initialization. Quantum computation begins with initializing qubits into a known starting state, often 0, 0 or 1, 1, 1. From this point, quantum gates are applied. Quantum gates. Just like classical computers use logic gates and or not, etc., quantum computers use quantum gates to manipulate qubits. However, these quantum gates are different because they operate on qubits' probability amplitudes, not just definite zeros and ones. Quantum gates like the Hadamard gate, Pauli gates, and CNOT gate help manipulate the qubit states in complex ways to perform calculations. The key advantage here is that quantum gates act on superposed states, enabling simultaneous manipulation of multiple potential outcomes. This leads to the potential for exponentially faster computations compared to classical gates. Measurement. The process of measuring a quantum state collapses the superposition of the qubits into one of the possible classical outcomes, 0 or 1. Due to the probabilistic nature of quantum states, repeated measurements may be required to obtain a statistically significant result. Quantum algorithms. Some specific quantum algorithms demonstrate how quantum computers can outperform classical systems in certain types of problems. Shor's algorithm, factoring large numbers. Peter Shor developed a quantum algorithm that can factor large integers exponentially faster than the best-known classical algorithms. Factoring is critical to the security of widely used encryption schemes like RSA, meaning a sufficiently powerful quantum computer could break encryption systems that classical computers cannot. Grover's algorithm. Database search. Grover's algorithm is a quantum algorithm designed to search unsorted databases with quadratic speedup over classical algorithms. While classical search algorithms need to examine each item one by one, Grover's algorithm uses quantum parallelism to search multiple database entries simultaneously, significantly speeding up the process. Quantum machine learning. Quantum computers are also expected to revolutionize machine learning. Quantum machine learning algorithms, like quantum-enhanced support vector machines or quantum neural networks, could process massive amounts of data and find complex patterns that classical algorithms might struggle with. Quantum hardware challenges. Building and operating quantum computers pose significant technical challenges, including qubit stability, decoherence. Quantum systems are highly sensitive to external influences like temperature, electromagnetic radiation, or even vibration, leading to decoherence, the loss of quantum information due to the collapse of quantum states. Keeping qubits in a coherent state for long enough to perform complex computations remains a major hurdle. Error correction. Quantum error correction is another major challenge. In classical computers, errors in bits can be corrected using redundancy, but in quantum systems, error correction is far more complicated due to the continuous nature of quantum states and the inability to copy qubits, no cloning theorem. Specialized algorithms and qubit configurations, such as surface codes, are being developed to address this issue. Scalability. Building a large-scale quantum computer requires thousands, if not millions, of qubits. Today's quantum computers are mostly small, with tens or hundreds of qubits. Scaling up the number of qubits while maintaining stability and error rates is a major technical barrier. Cryogenics. Many quantum computing systems need to be kept at extremely low temperatures, close to absolute zero, to function properly. Superconducting qubits, for example, only operate in these conditions, adding to the complexity and cost of building quantum computers. Potential applications. Quantum computing has the potential to revolutionize many industries. Cryptography. As mentioned earlier, quantum computers could break current cryptographic systems like RSA by factoring large numbers more efficiently. However, they could also enable new forms of encryption, such as quantum key distribution (QKD), which is theoretically secure against any computational attack. Drug discovery and molecular simulation. Quantum computers could vastly improve the simulation of molecular structures and interactions, which is essential for drug discovery and material science. Classical computers struggle with these simulations due to the complexity of quantum interactions within molecules, but quantum computers can model them natively. Optimization problems. Quantum computers can solve complex optimization problems much faster than classical computers. These problems appear in many fields, including logistics, e.g., optimizing delivery routes, finance, e.g., optimizing portfolios, and machine learning, e.g., optimizing neural networks. Artificial intelligence and machine learning. Quantum computers hold the potential to advance machine learning algorithms, making it possible to train models on larger datasets or with higher dimensionality. Quantum computers could provide a massive boost in pattern recognition, data clustering, and predictive analysis. Climate modeling. Climate modeling involves solving massive systems of differential equations to predict the future state of the climate. Quantum computers could simulate these complex systems more efficiently, helping scientists predict climate change more accurately. Current state and future of quantum computing. While the field of quantum computing is still in its infancy, companies like Google, IBM, Intel, and startups such as Rigetti and IonQ are making significant strides. Quantum supremacy. In 2019, Google announced that it had achieved quantum supremacy by demonstrating that its quantum computer could solve a problem faster than the most powerful classical supercomputers. This was a major milestone, although the problem solved was not particularly useful for real-world applications. The true potential of quantum computing will be realized once we develop algorithms that solve practical, large-scale problems better than classical systems. Near-term applications, NISQ era. We are currently in the noisy intermediate-scale quantum, NISQ era, where quantum computers with hundreds of qubits exist, but are still prone to errors. During this period, research is focusing on using these early quantum machines for tasks like optimization, simulation, and machine learning in ways that are hybrid with classical systems. Fully fault-tolerant quantum computing. The long-term goal is to develop fault-tolerant quantum computers that can perform large-scale computations without errors. This will likely require the development of more robust error correction methods and scalable qubit architectures. Conclusion: quantum computing is a fascinating and complex field that stands at the intersection of physics and computer science. It has the potential to revolutionize industries, solve previously unsolvable problems, and outperform classical computers on certain tasks. However, many challenges remain in the development of scalable, reliable quantum computers. As research continues to advance, quantum computing could redefine our technological capabilities in ways we cannot yet fully imagine.